we have no assurance that there would be any n that satisfies this condition. What this says, folks, the square root of this quotient is a fraction, is a rational number. In most cases, you pick an arbitrary n, and this is going to be an irrational number. But we want to find out if there are any n, find all of the n such that the square root of the quotient 9n minus 8 over 4n plus 5 is actually a rational number. Now, n equals 1 gives us a real simple example. Notice when you put n equals 1 in here, you would get the square root of 1 over 9. Okay, and so that, of course, is equal to 1/3, and that's a member of Q. 1/3 is a proper fraction. We'll write down a member of Q, where Q stands for the ratio of any pair of integers, other than 0, of course, in the denominator. Okay, so there we go, folks. So we know that there's at least one example. We're supposed to find all natural numbers n such that this can happen. We've already found one, so we know it's possible. All right. Now, there's a well-known result that I used to know how to prove. I can't prove it anymore. I'll just state it without a fact. It essentially says that the greatest common divisor of any pair of numbers divides any linear combination. Now, I should say right here that A and B are a member of Z. Okay, and that's just the integers. Okay, and there is a very well-known result from number theory that says the GCD can be represented as a linear combination of the two values. Now, just a word on the notation. Parentheses 15, 6 represents the greatest common divisor of 15 and 6. That would be 3. 3 is the largest integer that divides both 15 and 6. Okay, and so a lot of people like to put GCD in front of this, but you can represent it as just an ordered pair of numbers. Notice that it's the square root of 6, or excuse me, 6 comma 15 is equal to 15 comma 6. But in any event, that's what this means. It means that if you can always, any linear combination whatsoever of the two numbers is going to be a multiple of the greatest common divisor. And that turns out to be very, very useful because we can do a quick calculation and notice that if you multiply this first expression by -4 and the second expression by 9 in sum, the ends cancel out. We end up with 77. So we know that the GCD of these two numbers would be a number, would be in the set 1, 7, 11, and 77, which are the divisors of 77. And again, the GCD would be one of these numbers. In other words, these are the divisors of 77, and so those are our attempts when we're trying to solve this equation. Now, what we do is go ahead and set the numerator, like right here. I'll go ahead and just write this up here. You can write this as x over y, where x and y are rational numbers. And notice that if you square both sides, this is what happens. If you square both sides, you get this condition right here. So assuming that the numerator and denominator are relatively prime, we can write it like this because there's not going to be anything here that cancels, right? And so that's what I'm doing here. And you'll see the process here. When you multiply this out, you end up with this statement, okay? Notice this is the difference of two squares. Now, what I'm trying to convey here is that I'm actually using these divisors pairwise. See, we have 1 and 77 right here, all right? And so when you perform the arithmetic here, or when you perform the algebra, notice that what happens here is something fairly comfortable for us. When you sum up both of these guys, the two x's cancel, and you actually get 6y equals 278. And you could do that in any order and you would still get 6y. If you swap the 77 and the 1, wouldn't make any difference owing to the fact that when you sum them, the two x's cancel out. And so 6y is equal to 78. That implies y is equal to 13, okay? Well, let's take a look and what does that do for us, okay? If y is equal to 13, that means we can equate, let's just write it, y is equal to 13, so we can write down 4n plus 5 plus 5 equals to 13 squared. Okay, folks, again, we get y is equal to 13 from this difference of two squares result. And then we can put 13 right here where y squared is and equate it with this denominator. Okay, so this is 4n equals to, let's see, 13 squared is 169. 169 minus 5 is 164. So we would get 4n equals to 164. Right? Okay, and so what that tells us that n is equal to 41. N equals to 41. Now, y'all remember, this is our original expression we were working with. So what does this end up being? This would be equal to, and we have to check these to make sure it works out. There's no assurance it will necessarily work out. So we would have, this is equal to the square root. Now, 9 times 41, folks, is 360 plus 9. It's 369. 369 minus 8 is 361. Okay, so we have 361 in the numerator. Okay, now, right here, 4 times 41 is 164 plus 5 is 169. But notice 169 is equal to 13 times 13, 13 squared. And 361 is equal to 19 times 19. So what we get right here is the square root of 19 squared. And we can see the light here at the end of the tunnel, 19 squared over the square root of 13 squared. And we have an element that's certainly a member of Q. 19 over 13 is a member of Q. That's kind of cool. And I think I've covered my bases here. Now, y'all, this right here, you can verify this would lead to n equals 1 and what happened up here at the beginning, okay? When we notice by inspection at the very beginning that n equals 1 gives us 1/3. This second case here, y'all notice I used the other two divisors, 7 and 11 of 77, okay? And don't forget where that 77 came from. Okay, we used this linear combination result and then did a specific calculation that would eliminate the n's, leaving 77. And we know the GCD always has to divide 77. You may go, why are you talking about the GCD all the time? Well, that has a lot to do with whether or not a pair of fractions reduces. If you consider their GCD, if their GCD is 1, then the fraction is irreducible. If it's anything else, it is reducible. So, but in any event, we've gone through both cases. So this was kind of like a, I don't know how to put it, but a workhorse, so to speak, to produce a result that would give us a foundation in which to create an equation. And that's exactly what these two statements are, okay? So anyway, the non-trivial result was n equals 41, and the fraction associated with n equals 41 was 19 over 13 improper fraction, and it is the square root of a perfect square in Q. But I think that does it, folks. Hope you enjoyed the video.